Hello everyone, this is the continuation of our last video uploaded in YouTube in the name friction, and this will be the part 2 and most probably the last part. See, today's topic is work done against friction. So we know that friction work done is your force multiplied by some distance covered in the linear distance. Always remember the distance should be in linear form. The distance would be in linear form. If you have applied some force with an angle theta with the horizontal, then this force, either this force has some component, that is f cos theta, into, let us say, this displacement is center to center is s. So our work done would be f cos theta into s. This is our f dot s. So work done is a scalar quantity because it's a dot product. So this is the example of two vector quantities. Multiplication of two vector quantities is a scalar quantity. So let us continue. If we want to find out this work done against the friction in moving a object in the horizontal direction. So let us see, we are moving this object against the friction, that means our surface is a rough surface. We have moved this object to displacement s or distance s. So we know that mg will act through its center of gravity and it will have a reaction force, and if we are moving, we have applied a force P in the right hand side, so our friction would be on the left hand side, Fs. Now here our Fs is your static friction. We know we have three types of friction: static friction, dynamic friction and rolling friction. Static friction, kinetic friction, or dynamic friction, or rolling friction. So static friction depends on the force you have applied externally, and once the body has started moving, it will only have dynamic friction, that is kinetic friction. Now let us say this object moved the distance s, and the same component has been shown here. So what is the work done? Work done is force multiplied by displacement. Now see here, force is we are moving the object against the frictional force. So friction is a contact force, we already know. So Fk multiplied by s. Now see, we know that as the object is moving, so here we will apply kinetic friction, and Fk is mu k into r. Now see, r balances with mg, so mu k into mg. So W would be mu k mg s. Now if we move forward to our next topic, that is we want to find out the work done against the friction in the up the plane, up the inclined plane. If you want to find the up the inclined plane, so here we know the component resolve, that is mg will be perpendicular to the horizontal surface, that is towards the earth, from the earth, and this is your mg cos theta component, and this is your perpendicular component mg sin theta, and this is your reaction force according to the Newton's law. If the block is applying force, some force, it will give a reaction force. So this is Newton's third law, and we have applied a force P in the upward direction. So from this we can say that R is balancing out with mg cos theta, and P, see here P is in the right hand side, and the left hand side we have two components, that is, one is your mg sin theta acting downward, and it is pulling the object, it is trying to pull the object in the downward direction, and as well as the object is feeling a opposing force, that is Fk, that is frictional force. So we can say that P must be equals to mg sin theta plus Fk. Now Fk we know mu k into r, so r is your mg cos theta, so mu k into mg cos theta. Now put the values here, Fk, so P would be mg sin theta plus mu k mg cos theta. Now work done is force into displacement, so this is your force multiplied by distances. Now see what will happen if we apply the same force in the downward direction. If we apply the same force in the downward direction, then see, we have applied the force in the downward direction. Now this angle is theta, this angle would be theta, this is mg cos theta, and this would be your mg sin theta. And as the object is moving downward, so we have the frictional force, that is kinetic frictional force, in the upward direction. Now what will be the equation? Here also r equals to mg cos theta and p and mg sin theta acting downward, p and mg sin theta acting downward. So p plus mg sin theta would be your fk. Now we know fk equals to mu k into r. R is your mg cos theta, so mu k into mg cos theta. Now put the values here. So p would be fk, that is mu k mg cos theta minus mg sin theta. Now apply the same formula, W equals to force into displacement. Now force is this thing, mu k mg cos theta minus mg sin theta multiplied by displacement. Now if we want to find the acceleration, let us say the acceleration is downward, acceleration A. Now see, we know that force equals to mass into acceleration. Now this force will be, this is your force, so force would be your mass into acceleration. So mass into acceleration should be equals to this, mass into acceleration should be equals to mu k mg cos theta minus mg sin theta. Now take m common and cancel out, so you will get acceleration, mu k g cos theta minus g sin theta. This is the required acceleration. So by this thing, don't remember any formula here, because you have to derive this formula according to the component. Okay. Now let us see some example. See, here we have made a mistake, that is in the downward direction, in the resultant acceleration, resultant force, resultant acceleration is in the downward direction. So resultant force F net, what would be the F net that is acting downward? This should be mg sin theta is acting downward, so it will be greater force, and Fk is acting upward, so mg sin theta minus Fk. Now you put the values. F net is mass into acceleration, this is mg sin theta, minus Fk is your mu into r, and r is your mg cos theta, so mu into mg cos theta. Now take m common, you will get acceleration equals to g sin theta, or take g common, sin theta minus mu cos theta. Now let us see some example. Okay, let us see one problem. Here in this inclined plane, the arrangement is given as this block has mass 2 kg, this block has mass 5 kg, and it has an acceleration of a. Now see, we already know that if the string is same, then acceleration will also be same, and we also know, see here coefficient of friction is given, that is 0.3, so it is a rough plane. You have to find acceleration of the system and the tension in the string. See, we know that tension always acts towards the pulley, that is for the string, always remember, for the string force is away from the object, and if two objects are attached, let us see this, two objects are attached, and if you are applying a force here right hand side, so if you draw the free body diagram, you will see it is a pushing force. Let us see this. So for this object it's a push force, and tension, for tension always remember this, for tension it is a pull force. For attachment of the objects or attachment with any surface, it is a push force, and for any tension, for any wire or any tension, it's a pull force. That means, see, if we attached two objects with this string, So it's a pull force. So it will pull. So it's a pull force. Pull. Okay. Pull force. And it's a push force. So for two surfaces it will be a push force, and two objects attached with a string it will be a pull force. So here also see it's a tension, and it will give the same tension. The pulley will give the same tension. So it's a pull force. And here also it's a pull force. If you draw the FBD of this object separately, what will be the forces? Here 5 kg is the object mass. So here weight or force would be mg, that is 5 into g, and tension is acting upward P. So we can say that object is coming downward. So 5g is greater. So 5g minus T, that is the effective force. Effective force, that should be equals to mass into acceleration. So 5 into A. Now let us see this object. It has the same component we have seen in the previous slide. So it's a 2 kg mass. So it will be 2g. The weight is 2g. It will be 2g cos theta, and perpendicular component will be 2g sin theta. As the object is moving upward, it will have a frictional force in the downward. So what is the net force here? Net force here, as the object is moving upward, so this tension will be larger. So T minus g sin theta minus F should be, this is the net force, that should be equals to mass into acceleration, that is 2 into A. And we know F equals to mu into R, and R is your mg cos theta, that is 2g cos theta. Now you know the value of mu, g m cos theta. Find the value, put the value of F here, and solve 1 and 2 equation. You will get acceleration as this and tension as 24.65 meter per second square. Solve individually. Now see next question. A body of mass m is released from the top of a rough inclined plane. So this is the mass m. You have released the object. If the force of friction be F, then prove that the body will reach the bottom with a velocity given by this. Always remember, for this type of problem, see the body is from h height from the ground, right? The body is in h height from the ground. So if it has a height, then it will have a potential energy. So it will have a potential energy of mgh. If you release the object, that potential energy is going to convert into kinetic energy. So kinetic energy would be half mv square. So what is the loss of energy? Loss of energy would be mgh minus half mv square. Now this loss of energy will convert it into work done, because we know work done is also a energy. So this loss of energy will get converted to work done. Now this work done is against the frictional work done. So friction is acting upward. So F multiplied by distance. So let us say it will move to the bottom. So it will cover the total distance. So F into L, force into displacement, would be your work done. So half mv square is this, V equals to this. So remember the types of problem, because in the friction, work for energy, Newton's law of motion, kinematics, the logic is important. How many types of problem you have done, that is important. How much problem you have done, that is not important. So try to build your own logic. Only the logics will help you. Now let's go to the next topic. So let us see another question. It is easier to pull a object than to push. So you have to prove it, that it is easier to pull a object than to push. So here in this arrangement, so it's a roller. So we are showing the front end only. So it's a roller, you are pulling with the handle, and it's a roller, you are pushing with the handle. Okay. So if you are pulling with the handle, that is if you are applying the force F towards yourself. So let us see, the force F is this, and the roller is attached to the ground. It is moving in the right hand side. So frictional force will act in the left hand side, and as it is connected to the ground, so it will have a reaction force R. So let us say this F is making an angle theta with the horizontal. So this component would be F cos theta, and the perpendicular component would be F sin theta. Now see here, R is acting upward, F sin theta is acting upward, and W is acting downward. So r plus f sin theta should be equals to w. This is your equation number 1. So r should be equals to w minus f sin theta, and we know f equals to mu into r, and r is w minus f sin theta. Keep this thing as it is. Now we are pushing the roller with this handle. So this, the effect is towards the center, so this will be your f. Now let us say this angle, let us say this angle, this force is making angle theta. So vertically opposite angle, this would be the vertically opposite angle theta. So this is f, so this component would be f cos theta, and perpendicular component would be f sin theta. Now here balance, this r prime is acting upward, f sin theta is acting downward, fk is acting in the left hand side because the roller is moving in the right hand side. So we can say this r prime equals, and weight is acting downward, w plus f sin theta. Now fk prime, let us say mu k into r prime, and we know r prime w plus f sin theta. So in the final expression, if you compare the frictional force, that is the opposing force, in this where you are pulling the object, there is a w minus f sin theta component. That means the f sin theta component is deducted from the net weight, and in this component f sin theta component is added with the net weight. So this fk prime will be larger than this fk. So hence it is proved that it is easier to pull the object because here f sin theta component is deducted. So let us move forward to our next topic, that is centripetal force. It will require in our banking of road and cyclist, this type of problem. So centripetal force is a force required to make a body move along a circular path with uniform speed. With uniform speed, that means it is falls under uniform circular motion, UCM. So in uniform circular motion, velocity, the magnitude of velocity always same, direction changes. So that's why in this case we have only tangential acceleration. We don't have any centripetal acceleration. It's also called centripetal force. It acts along the radius, so its direction will be always towards the center. That's all you have to remember. The direction of that force is towards the center, and that force is given by mr omega square or mv square by r. Here omega is your angular velocity. Angular velocity, that means angular displacement by time. Theta is your angular displacement. See, if you are moving an object from this position to this position, so it had moved some angle. If you are moving that object from this position to this position, so it had moved some angle. As it is moving some angle, so we call it angular displacement. So angular displacement is your theta. So velocity is actually our displacement by time. So angular velocity would be your angular displacement by time. So it will be our omega is our d theta by dt. All rest of the terms you know. Now let us see one problem. A ball of mass 0.1 kg is suspended by a string 30 cm long, keeping the string always taut. That means it is stressed. The ball describes a horizontal radius circle of radius 15 cm. Calculate the angular speed. That means the diagram is something given like this. The ball is attached in this position. The length of the string is 30 cm. The circle in which the object is, the ball is moving around something like this, that circular path has the radius of 15 cm. Now see, tension is always away from the block. So here the block or the object is this, so away from the block. So this is our tension T in the string. Let us say this angle is theta. So let us draw a parallel line. This is your transversal. So this angle would be alternate angle theta. So as this is T attached with this theta, so this component would be T cos theta, and the perpendicular component would be T sin theta. Now see, centripetal force is acts towards the center. That means this component is your mv square by r or mr omega square. In uniform circular motion, we will see that this force actually it depends on inertial frame and non-inertial frame. For inertial frame we use uniform circular motion. That means for inertial frame you are standing outside this experiment and you are seeing that object revolving in a circle of radius, let us say radius r. That's why this is mr omega square or mv square by r. That r is the radius. So for inertial frame, that is you are lying on a fixed surface which is not moving or which is not accelerated. For inertial frame you see that the object is moving due to this force. Due to this force the object can move in the circular path. But for non-inertial frame, that is whenever you are lying on the object, you are on the system and the system is moving. In that case we say that we are applying that thing is known as a non-inertial frame, because our frame is also moving with the acceleration, let us say with the acceleration a. So in that scenario we will see that the object is at rest. So let us say we are on the earth. So we actually take our earth as an inertial frame, but actually the earth is moving with respect to some other planets. So with respect to earth, that is inertial frame, but with respect to other planet, we are not inertial, we are non-inertial frame, because we are also moving with the earth. So that's why as we are moving with the same speed, the earth is moving, that's why earth is seen to us as a rest, and we call that thing as a inertial frame. But whenever there is a non-inertial frame, that means you are on the system and the system and you, both of them are moving with the same acceleration or same velocity. In that case we call that there is a, whenever you are lying on that system, you don't see this mv square by r, you see the outward force which is mr omega square. So this is for non-inertial frame. It is also called pseudo force. So pseudo force comes into picture whenever you are on the system, and that system is known as a non-inertial frame. That means you are accelerated, you are also accelerated with the system. But here in this uniform circular motion case, you are lying outside the object and you are seeing the object is revolving. So in that case we will apply mv square by r, and that mv square by r is acting towards the center. But for non-inertial frame the same force is applying, but outward to the center. That thing you have to remember. So remember this: inertial frame and a non-inertial frame. Remember this. The force is same. For inertial frame, centripetal force is mv square by r, and for non-inertial frame we call it centrifugal force. Not centripetal force, centrifugal force, and that is also mr omega square or mv square by r, but it is acting outward. But for inertial frame it is acting towards the center. That's the thing you have to know. Now see, this should be your inertial frame, because you are observing this object from outside, okay, and wherever you are staying, that thing is fixed, only acceleration is in this object. So you are lying on the inertial frame, you are observing this thing rotating. So that means this sin theta component is giving this required force to move in the circular path constantly. So this t sin theta component is acting towards the center. So that means this component should give your centripetal force. So our t sin theta is your mr omega square, and from this component result we see that t cos theta is equivalent to mg. These are balancing out each other. Now from this triangle find out sin theta. We know this component, we know this component, opposite by hypotenuse, that is 15 by 30, half. Now half is for 30 degree, sin 30 degree is half, we know, that means theta is 30 degree. Now divide these two things, you will get tan theta equals to r omega square by g. So omega would be g tan theta by r. Now you know the value of theta, that is 30 degree, so tan 30 degree, and g is 10 and r is 0.15 meter. Always convert in SI units, otherwise answer would be wrong. And angular, this is angular velocity. So angular velocity is angular displacement by time. Now what is angular displacement, here the unit is radian. Here we have time, so radian per second is the unit. Let us see the circular motion on banked road. Now see, the system of raising the outer edge of a curved road above its inner edge is called banking. See, this is a curvical road that is circular and it is above the surface, that means see, this is the banking, this is your banking. So the angle is, the banked angle is theta, and the angle is known as the angle of banking. Angle of banking is theta. So in normal scenario, the surface of the road actually banked to a some angle in order to avoid the friction and wear and tear of the car. Let us see how it acts. See, this is the circular path, the car is moving, this is the circular path, the car is moving, and the surface is banked to angle theta. So it is in the height angle theta. This is our car, and we will have reaction force R1 and R2. We have taken the resultant reaction force as R. Let us say that our resultant reaction force is R. Now see, this angle is theta, so this, draw a horizontal line. So this angle will be this angle theta, so that means this angle will be theta, we know this angle will be theta. So this is a vertically opposite angle, this angle will also be theta. Now our reaction force is making angle theta, so this component would be r cos theta, and this component acting towards the center will be r sin theta. Now for frictional force, if you draw the friction something like this, and if you extend this arm, so you see this angle and this angle vertically opposite angle, so this component would be f cos theta and this component would be f sin theta. Now let us balance all the components. In the centripetal force, that is towards the center, see this force is towards the center, this f cos theta is towards the center, so r sin theta, this r sin theta and f cos theta, these two are giving the required centripetal force, that is mv square by r. Now see this vertical components, f sin theta is acting downward, r cos theta is acting upward, so f and mg is acting downward. So mg plus f sin theta should balance with r cos theta. Mg plus f sin theta is balancing out with r cos theta, and we know f equals to mu into r. So r cos theta would be, so r cos theta minus f sin theta should be equals to mg, divide 1 and 2, you will get something like this, r sin theta plus f cos theta by r cos theta minus f sin theta equals to v square by rg, here mm will cancel out. Now divide numerator and denominator by r cos theta, by r cos theta we are dividing, so r sin theta by r cos theta, r cancel out, this will be tan theta, f cos theta and r cos theta cancel out. Now we will have f by r, and here r cos theta cancel out and f by r tan theta equals to v square by r. Now this is known as maximum velocity by which the car can move in a circular banked road. Remember this as a formula also. This is the maximum velocity of this car to move without slipping in a curved banked road. Rg multiplied by mu plus tan theta divided by 1 minus mu tan theta. Now see, if the frictional force is 0 in the rainy season, the friction between the tires and the road is extremely low. So we can say that in the rainy season or in the muddy road or in the sand road, the friction decreases. So let us say that friction coefficient of friction, let us say, is 0. So if mu is 0, here, mu is 0, this term would cancel out. So we will have Rg tan theta. So in frictionless surface, our maximum velocity by which the car can move is Rg tan theta. This is the advantage of banking. See here, we have make the road frictionless in the rainy season or in the muddy road area, but still we have some velocity of the car, that is root under Rg tan theta. That's why the banking of road is extremely important in order to avoid slipping. Okay. This is extremely important. And if the angle of the banking theta for minimum wear and tear, so if you put mu equals to 0 here, this would be tan theta. From here we can say that V square by Rg should be equals to tan theta. So this is the minimum angle. This is the minimum angle for which for minimum wear and tear of the tires. So this topic is extremely important. See, if the scenario, if we want to redraw the scenario for leveled road. So for leveled road, the angle, this theta angle would be 0. So if theta angle would be 0, this will gone, this term will gone. So we will get V max equals to root under mu Rg. This is the case for leveled road. For level road, we made theta equals to 0. That means this theta 0. If we make theta 0, tan 0 0, this mu tan 0 will gone. So Rg mu Rg. But look at this case. If we make the road frictionless, that is for muddy road or for sanding road or in the rainy season, mu will be almost 0. So there mu is 0, so velocity would be 0. So that means there is a chance of slipping. Okay. Now see, if this friction, this centripetal force is not there, if the tires do not give the proper centripetal force required to move in the curved banked road, then it will move in the outward. So that's why the car, whenever the car slips, it moves away from the road in the right hand side. Okay, that's all you have to remember for banked road. So let us move forward our logic of bending. Now see here, bending of a cyclist. Let us see the case. If we bend the cycle, we everyone have ride on cycle. We observe that whenever we move in a circular path or whenever we want to move in the right hand side or left hand side, we lean inwards. There is the reason, because see, actually that frictional force of the tire gives the necessary centripetal force. We know that. But for bending of cycle, the necessary frictional force is not exactly same as mv square by r. That is, it doesn't give the necessary centripetal force required to move in a circular track. For that, the cyclist lean inwards. See, our cycle is leaning inwards from the vertical, inwards. Why? See, the reaction force as the tire, this is the tire with the horizontal. Now this tire is, this surface is giving some reaction force. Now this is our reaction force of the tire. Now if you observe the angle, this is parallel line, this is the transversal. Now this angle and this angle, this whole angle and this angle theta, same. So the component of reaction force, this is r cos theta and this is your r sin theta. That's why we have leaned inwards, because now our leaning, that means our r sin theta component will give the necessary centripetal force to move in a circular track of the cycle. So from the diagram we can see that this r sin theta is giving your necessary centripetal force, that is mv square by r, and this r cos theta is balancing out with mg. Now divide these two things, r sin theta by r cos theta, mv square by mg. Now here you see that tan theta is v square by rg. That is the angle you have to bend to give the necessary centripetal force in order for the safe ride. Okay. Now let us see one example. So let us see our next topic, which is UCM, uniform circular motion. A particle moves along a circular path with a constant speed. That means speed is constant, but its direction is changing with time. Then its motion is said to be a uniform motion. Now what is angular displacement? Angular displacement is the angle by which the object travels in the means of its radius vector. Here r is our radius vector. So theta is given by s by r, that is linear displacement by r. Now angular velocity is d theta by dt, that is angular displacement by time is your angular velocity. This angular displacement from, let us say this is theta 1 by theta 2. So theta 2 minus theta 1 by t2 minus t1. If that object moves from this position to this position in, let us say, in t2 time here, in t1 time here, so this angle, let us say theta 2, this angle, let us say theta 1. So it actually covers theta 2 minus theta 1 divided by t2 minus t1, which is your angular velocity. The frequency is 1 by time period, we know. Now angular velocity is angular displacement by time. Now what is the angular displacement of a object to cover one circle? To cover one circle, that is the total angular displacement is 2 pi by t. So 1 by t is f, 1 by t is nu or f, so this is 2 pi nu. So omega equals to 2 pi f or 2 pi nu. Remember this. Now we have another relation, we don't have to derive these things, this is not in our syllabus, but we will use these relations. So this is the relation between linear velocity and angular velocity, that is v equals to omega into r. R is the radius vector, remember. And angular, there is a relation between angular acceleration and linear acceleration. This a is your linear acceleration and this alpha is your angular acceleration. Now if you want to derive, what is angular acceleration? That is angular velocity by time. This is same as linear acceleration, right? Acceleration is velocity by time, so here it is angular acceleration, so angular velocity by time. Now centripetal acceleration, this acceleration is your centripetal acceleration. Remember this is v square by r, and you can denote this as c also or r also, because remember that centripetal acceleration acts towards the radius or towards the normal of the tangent. So centripetal acceleration is towards the center or radius, so that's why it is denoted AC or AR, that is v square by r or omega square r. Now v equals to omega r, we know v equals to omega r, so put this v equals to omega r, omega square r square 1 r will get cancelled out, so we will get AC equals to omega square r. All these cases are for uniform acceleration, that is speed is constant. Speed is constant throughout the motion. Speed is constant throughout the motion. Velocity is changing for the direction. Speed is constant throughout the motion, throughout the circular motion. Velocity is changing because of the direction, but magnitude of speed is same in all the points. So for variable speed, if we have speed is variable, see the term, it is speed. If the speed itself is variable, then we will have two components of acceleration. One component is your centripetal acceleration, which is denoted as AR or AC, and another acceleration would be your tangential acceleration. Tangential, this is the tangent, so tangential acceleration, AT. So resultant between tangential acceleration and centripetal acceleration, that is this. If you add vector or triangle law of addition or parallelogram law of addition, you will get the resultant acceleration would be root under of AT square plus AR square. See here AT and AR are perpendicular, so 2 AT AR cos theta, the term will be omitted out. Now if you want to relate from the linear motion equation, that is v is equal to u plus AT, v square is equal to u square plus 2as, s equals to ut plus half AT square with the angular velocity. See here v is the final velocity, so let us say in the angular motion the final velocity is omega, right, and initial velocity, let us say initial angular velocity is omega naught, plus a is linear acceleration. What would be angular acceleration? Angular acceleration is alpha t, that is the first equation motion. Second, let us say v square, that is omega square equals to u square, initial velocity, so here we will have initial angular velocity, which is omega naught square, plus to a is angular acceleration, that is alpha, s is linear displacement, here we will have angular displacement, which is theta. So 2 alpha theta, and in the third equation s equals to ut plus half at square. So s is linear displacement, here we will have angular displacement theta, u is your linear velocity, so here we will have angular initial velocity omega naught t plus half a, so here we will have alpha t square. So remember this equation, these equations are for uniform circular motion. Remember this is for your uniform circular motion, that means speed should be constant throughout the motion. If the speed is constant, only then the acceleration is constant, speed is constant, that means acceleration is 0. So for uniform motion, only for uniform motion, that's why the heading uniform circular motion, that means speed is constant throughout the motion. If the speed is constant, only then you can apply these equations as we have applied for constant motion, for linear motion, right? These equations are equivalent to circular motion. So hope you are enjoying it. So we have covered maximum number of topics in the board level. In the JE level or in the advanced level, we will see more topics like this. So please like, share and subscribe. Thank you.